This test instrument is generically known as a curve tracer. Its purpose is to plot the voltage versus current characteristics for a two-lead component. Currently we have a red lead plugged into the A jack and a black lead into the common jack, and presently these two test leads are open. There's nothing connected between them. So what this is showing us is as the device is sweeping an AC voltage between these two test points, it's showing us the applied AC voltage on the horizontal axis. Off to the right, that's where the red is positive and the common is negative. On to the left, that's where the polarity is reversed, where the red is negative and the common black is positive. Currently, because there's nothing connected between the test leads, we have an open, and therefore that guarantees a condition of zero current. So there's no vertical displacement at all on that graph. If we were to short these two leads together, what we have now is a vertical line showing us the presence of current with minimal voltage. So as it attempts to sweep an AC voltage, positive and negative, instead we see a short circuit condition where we get maximum current with very, very little applied voltage. So vertical line, shorted, and horizontal line means open. Okay, well that's all well and good, but how do we actually test components? Well, let's take a very simple component, in this case a 6.8 kilo ohm resistor. We will connect our test leads to the resistor as such. And as you see, we get a tilted line. It's linear, and we can change the pitch of that line by changing the range of the device. It's definitely a linear response, and this makes sense for a resistor. As we apply voltage in one polarity, we get current in one direction. So we have the upper right-hand quadrant with that part of the line there. As we apply voltage in the other polarity, we get current in the other direction. So we get a nice linear response. That's exactly what we'd expect for a resistor. Now, things get more interesting if we connect a semiconductor component, such as a diode, across the same two leads. So I'm going to clip the red lead to the anode and the black lead to the cathode. And what we get here is a characteristic hockey stick sort of response from this diode, meaning that as we apply a forward bias voltage on the right-hand side of the vertical line, we don't have to apply very much voltage at all to get a significant amount of current going through that diode. And then as the polarity switches and we apply a reverse bias voltage across the diode, we get no current at all, or at least minimal. And so we see practically a flat line here at the zero mark, but a very sharp upward rise here, showing proper forward conduction. And of course, if this diode were damaged, we could test that by the same response. If the diode were failed open, we would see a flat line all the way across, just like an open condition here. If the diode were failed shorted, we'd see something that looked more like a vertical line. We can also see a more interesting response if we connect a Zener diode between the same two test leads. So here we go with the Zener diode. Zener diodes, of course, are known for their ability to break down in the reverse bias region. So here we see the normal rectifying diode response in the forward bias region of the graph, but then in the reverse bias section, we see that it maintains practically zero current for a significant amount of applied voltage, and then at a certain point it breaks down, and we see a reverse current begin to flow. So that's showing us the proper behavior of a Zener diode. And again, we can change the range here, get different scales. We can also connect different types of passive components to this tracking device. For example, a capacitor. Now the response I get from a capacitor looks really strange at first. You may be wondering, where do we get this oval or circular pattern? Well, recall that when you apply an AC voltage, a sine wave, across a capacitor, you get a current that is 90 degrees out of phase. And if you map that out on Cartesian coordinates, if you drive a dot around a graph like this, where the horizontal has been driven by a sine wave and the vertical has been driven by a cosine wave, or any other two sinusoids that are 90 degrees apart, you will find it does trace a circle. So this circular pattern is showing us that this actually does have a 90-degree phase shift between voltage and current, as we would expect. I can also change the frequency on the tracking device here from power line frequency to 400 Hertz to 2000 Hertz, And as we do this, we see what looks like a more and more vertical line. In other words, we're seeing more current for less applied voltage. This too makes sense when we consider how capacitors react to different frequencies. As we increase frequency, the capacitive reactance goes down. That is to say, it has fewer ohms of capacitive reactance. That means more current for less applied voltage. As we decrease frequency, the reactance increases. We get more ohms of reactance at the capacitor, which means fewer amps of current for more volts of applied voltage. We can also clip in a small inductor and see how that behaves. Now, similar to the capacitor, we would expect a 90-degree phase shift between current and voltage. And indeed, we see something kind of like that. We see the beginnings of an oval, but in this particular case, we don't see much effect until we increase the frequency significantly. By increasing frequency with an inductor, we cause it to have more reactance, that is, more ohms of opposition. As we decrease frequency, we have less reactance, fewer ohms, that is to say, more current for less applied voltage. So that oval grows wider and shorter as we increase frequency. You'll notice, though, as we decrease frequency, down and down, the curve does not go to a vertical orientation. It has sort of a cant to it. And that makes sense because we know how inductors are built. They're built out of large lengths of wire. And those large lengths of wire, long lengths of wire, can have significant resistance. So there is parasitic resistance in this inductor, and that is accounting for that tilt in the line. Just as when we connected a plain old resistor to the two test leads, we saw a diagonal line showing us the resistive characteristics. Voltage in one polarity, current goes up. Voltage in the other polarity, current goes in the opposite direction. So we are seeing that same characteristic parasitic to the inductor by virtue of the fact that it has a fair amount of built-in resistance. So, in summary, this Huntron Tracker, the Huntron is the brand name, Tracker 2000 is the model. This is a curve tracing device, and it's basically a special purpose oscilloscope where it plots applied voltage on the horizontal and component current of the vertical to allow us to look at the characteristic curves of different types of components.